together.
All right. Oh, Dante is here, not absent.
What?
All right.
Crazy.
I'm such a nerd, but at least I'm having fun. All right. So, 3.2 polynomial functions in their graph. We already said polynomials are functions with whole number, non-negative exponents, right? Whole number, non-negative exponents. We talked about examples. We talked about what the graph looks like, right? The graph is smooth and continuous, no corners, no breaks. Then we talked about the end behavior of the graph. Even degree, both ends point in the same way. Odd degree, opposite directions, and then the lead coefficient tells us more. So we checked it out. And then we found the zeros, right? When we find the zeros, that's the x-intercepts. And we can do that by setting the function equal to 0 and solving. These were already factored. Some of these were already factored. Some of these were not. The thing is that we set them equal to 0 and solve. All right. And then we went on to talk about multiplicity of zeros. So multiplicity and x-intercepts. So the multiplicity is the number of times the root appears or the exponent on the factor. The exponent on the factor. Okay, so if r is a 0 of even multiplicity, oh, here's an example. If r is a 0 of even multiplicity, that's like this one, right? Here, the power on my factor, the exponent on my factor is 2. 2 is even. Okay, so if r is a 0 of even multiplicity, like this, then the graph touches the x-axis. If r is a root of odd multiplicity, like this, x equals -2, my exponent on the factor is 1. 1 is odd. Odd multiplicity means it crosses, right? And you can think of that kind of like a line, right? Y equals mx plus b, y equals 5x. That's a root, multiplicity 1, so it crosses. X squared, we already talked about it. It's a quadratic. It's a parabola. X squared touches the x-axis at x equals 0, and it bounces off. It doesn't cross it. It bounces off. Okay? The higher the multiplicity, the more the graph flattens out at that root. Okay? So if you have multiplicity 1, it crosses like this. If you have multiplicity 3, maybe it crosses like this, more like a cubic. Multiplicity 5 makes it even wider. So the crossing gets wider, flattens out. All right, so let's do these examples. So determine the multiplicity of each 0 and whether the graph crosses or touches the x-axis. So here I have multiplicity 1. So the root x plus 2 equals 0. It crosses at x equals -2. Odd multiplicity means it crosses the x-axis. Here, multiplicity 2 means it touches at x equals -4, right? If I take this and set it equal to 0 and solve, I get x equals -4. And we already did these ones on the previous page, right? We found the roots here. Now we're talking about the multiplicity of the roots. What about here? Multiplicity 1. So I'm just looking at the exponent on the factor, right? Multiplicity 1, so it crosses at x equals 1/2. Here, multiplicity 3. Thank you. Multiplicity 3 crosses at x equals 4. So odd multiplicity or even multiplicity, that's what I'm looking at, whether it touches or crosses. Multiplicity is the exponent on the factor, or the number of times the root appears. Okay? Something hard to see?
No, I was just...
Okay. All right, so you guys do 15 and 16. 15 and 16 we factored on the previous page.
So for the number where it crosses off,
Mhm.
is that, do you like always flip the sign?
So that's the roots, right? We already took that term, set it equal to 0 and solved.
Yeah.
So you are flipping the signs if it's linear,
Okay.
right? Yeah. But that's because you're setting it equal to 0, then you're subtracting that from both sides or adding it to both sides, right?
Yeah.
Okay. All right, you guys can do 15 and 16, right? Do you guys get it? Okay, who can factor 15 for me? We did this last class, right? This is x times x minus 1 squared. So that means it multiplicity on x. What's the exponent on x? That's 1. Multiplicity 1 crosses. At x equals 0. Crosses at that root. The multiplicity is the power on the exponent, and it crosses at the root. Multiplicity 2 touches. At the root is x equals 1. Here we factored this one. We got x plus 5, x plus 3, x minus 3. All multiplicity 1. Crosses. All right. Intermediate value theorem. Let f be a polynomial function with real coefficients if f of a and f of b have opposite signs. Then there is at least one value c such that a is less than c is less than b and f of c equals 0. What? What does that mean? What are we looking at? Who's got a guess what this means?
Wouldn't you have to look at the coefficients first, since it's saying, like, never mind, I don't know.
So the first part is let f be a polynomial function with real coefficients. Okay, so polynomial functions means I have my variable to non-negative whole number powers, okay? So that's what my functions look like. So I don't have to do anything with that. I just have to make sure I'm talking about polynomial functions. If f of a and f of b have opposite signs, what's f of a, what's f of b? What's f of x? It's a y value, right? So f of a and f of b are y values. If they have opposite signs, one's below the x-axis, one's above the x-axis, right? Okay? Then there is at least one value c between a and b, between your two x values. Your x values have opposite signs, or your y values have opposite signs at those x values, such that f of c equals 0. Does that make sense? So f of c equals 0 means it crosses the x-axis, right? It means it's a root. So let's draw a picture. Okay, let's say this is A, let's say this is B. F of A, F of B have opposite signs, whether they're both plus or both minus, doesn't matter. So this is F of A, this is F of B. Tell me something about the graph of a polynomial. No breaks, okay, good. So it's continuous, right? Which means I can draw it without lifting my pencil. If I connect these 2 points without lifting my pencil, I have to cross the x-axis, right? I have to have some point in here where my y value is going to be 0. That's all it's saying, right? It makes total sense. Once you draw a picture, it's like, why do I even need to write this theorem down, right? If my y values have opposite signs, f of A and f of B have opposite signs, one's below the x-axis, one's above, whether it's this way or whether it's this way, I don't care. Polynomial functions are continuous, so I'm not going to have something like this, right? That's not a polynomial. If I have polynomial functions, it's continuous. That means I somehow connect these dots. It doesn't matter how I connect them, right? I could connect them like this, and that's still a polynomial, but at some point it's going to cross the x-axis. That's it. Right? Kind of boring once you draw the picture. So this says, use the intermediate value theorem to show the polynomial functions have zeros between the given values. So what do I need to do? So I just need to say, okay, it's a polynomial. Yep. Whole number, non-negative exponents. Okay, we have a polynomial. We have a polynomial function. So I need to check x equals 1, and I need to check x equals 2. If I can show that those are opposite signs when I plug them in, then there is a root in between them. I don't care what the root is. So what did you get? Okay. So by intermediate value theorem, IVT, there is a root. There is a root between x equals 1 and x equals 2. I have a continuous function. This isn't only true for polynomials. This is true for any continuous function. If I have one negative and one positive, and I have to get between those 2 points without lifting my pencil, I'm going to cross the x-axis, right? So number 18 is the same. So I'm going to skip it. It's the exact same. I would write the exact same thing. I'll scan it in my notes. Where did she get what, Joe? What?
Nothing. I thought that said something. This just says 1 and 2.
1 and 2. Okay. Next topic, turning points in polynomial functions. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. Cool. What's a turning point? What?
Isn't that where like the graph?
Give it a shot, girl.
Isn't that where like isn't the turning point like where the graph like turns up and down?
Good. So where the graph changes from going up to going down. What are the words we used for going up and going down before in math? What does going up mean? Increasing. Good. So increasing means left to right going up, where it changes from increasing, and what's the going down? Decreasing. So we talked about intervals of increasing and decreasing before, right? So a turning point is where it changes from increasing to decreasing or decreasing to increasing. So Morgan, you knew. Don't stop yourself. Can all put it together, right? Okay, so I don't know if I saw people write down what a turning point is. I didn't write it down. That means you need to write it down, right? A turning point is where it changes from increasing to decreasing or decreasing to increasing. So if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. And I think Kaylani kind of talked about this last class with how you could figure out the graphs of functions. Is that right? Somebody talked about it. I thought it was her. Okay. Okay, so now we're going to graph polynomials without a calculator, right? Can we graph a polynomial without a calculator? Yeah, we just did a bunch of stuff that tells us how to graph these functions. Okay, so let's do it. Okay, so given a polynomial, this is a polynomial of degree n, right? N is a whole number, a sub n, x to the n, plus a sub n minus 1, x to the n minus 1. N is a whole number, positive whole number, so this is a polynomial. Use the lead coefficient test to determine the graph's end behavior. That's what we did at first, right? Even degree, both pointing in the same way, odd degree pointing in opposite ways, and then we look at the lead coefficient. 2, find x-intercepts. By setting f of x equal to 0 and solving the resulting polynomial, blah, blah, blah. Find x-intercepts means y equals 0, right? This is too wordy. I'm going to change it for next time, but it's way too wordy for me. And then check multiplicity. Right? If the factor appears an even number of times, it touches the x-axis. The factor appears an odd number of times, it crosses the x-axis, right? So that's multiplicity. So find the roots and check for multiplicity. 3, find the y-intercept by computing f of 0. Y-intercept means x equals 0. That's what we're trying to find, right? Y-intercept is x equals 0. X-intercept is y equals 0. Use symmetry. So this is something we talked about in a previous section, is symmetry, right? Symmetric with respect to the y-axis, symmetric with respect to the x-axis, to the origin, And then use the fact that the maximum number of turning points in the graph is n minus 1, where n is the degree of the polynomial function. All right, let's do it. All right, example, graph the following. So f of x equals x cubed plus 2x minus 4x minus 4. Okay, first we're going to talk about the degree. What's the degree? 3, because 3 is the highest power that appears. That means, what about end behavior? Same way, opposite ways. Odd degree is opposite directions, right? Okay, what's my lead coefficient? Lead coefficient is 1, which is positive, so that means my end behavior is like this. I don't know what's happened in the middle yet, but I know my ends look something like that, right? 2, I need to find the x-intercepts, so find the roots. So I set it equal to 0. gosh, that's too many words. Okay? Who can help me? What'd you do? Factor by grouping. Good, Morgan. So what can I factor common out of the first two terms? Good, x squared, and you're left with x plus 1. What can you factor common out of the second two terms? Negative 4, and you're left with x plus 1. Okay, so now only because you have x plus 1 and x plus 1, now you can factor out the x plus 1, right? So can I factor any more? How? So x squared minus 4 is the difference of perfect squares. I have a perfect square minus a perfect square. That factors to the difference of perfect squares. So I set each of these terms equal to 0 to find the roots. And I get my roots are x equals negative 1, x equals 2, x equals negative 2. So here I'm going to draw what I have so far. Bless you. I have the end behavior like this. If you have a pencil, draw this part in pencil, because I'm going to erase this at the end. Okay, I have the points x equals negative 1, 0, x equals 2, negative 1, and x equals negative 2. Okay, talk to me about multiplicity. What's the multiplicity of these roots? They're all 1, so they all cross the x-axis, right? So I know it's going to be something like this, right? In order to connect the dots, I'm going to have to do something like this. I'm going to do something like this, something like this, something like this, right? So that's my approximate shape so far, right? Is that clear why it's like that? So it crosses the x-axis at those points. It doesn't bounce off. I'm kind of playing connect the dots, right? I have to start here and connect the dots and cross the x-axis. All right, let's get a little more information before we fully draw it. 3 is y-intercept, which means set x equal to 0. So if I do f of 0, that equals negative 4, right? I don't need to write 0 every time. All these x's become 0, that's negative 4, so that gives me another point of 0, negative 4. All right, number 4. So I know on the last test I asked people if functions were odd or even, and a lot of people did not show work, right? So let's not show work now. What do you guys think? Is this odd or even or neither? Why?
Just taking a wild guess, maybe it has to do with the exponents.
It has to do with the exponents, right? Here I have odd exponents and even exponents. So it's going to be neither. And you can kind of tell that from the graph, right? If a function is even and I had one point here, it should be the mirrored point over here, right? Same thing with odd. You'd have a symmetry with points. And I don't have that, right?
So neither because the exponents are both odd, neither.
Mm-hmm. But if you look at something like like a different one and you can't see that right away, you might want to check it. But that was a really good explanation. If you think that it might be even or odd, you might want to check it. But I don't really feel like number 4 is a super necessary part of this. I feel like 1, 2, 3, and 5. I feel like 4 isn't super necessary. All right, 5. So what's the maximum number of turning points? How did you get that, Josie? Good. 1 less than the degree. So the degree is 3. Means you have a maximum of 2 turning points. Okay, so I'm going to connect these now. I'm playing connect the dots. Maybe this isn't exactly a minimum. Maybe it's over here. I'm not sure, but this is good enough based on the information that we have. Okay. All right, let's do number 20. So do you guys feel okay about this? Maybe? Was this on the homework a lot? Oh, really? Yeah, it's hard to just say graph it, right? Yeah. So it's, sometimes the graphing is multiple choice. Yeah. All right, let's try number 20. So first, what's the degree? Ooh, I don't know about 2. Some people are saying 2, some people are saying 3. What happens when I distribute and multiply all this out? I'm going to have x to the what power? Well, here I have x squared. I'm going to have it times x times x. So what's x squared times x times x? X to the 4th. Degree 4. Oh man, I can't spell. Lead coefficient. So now I'm looking for the number that's going to be next to x squared. So if I do negative x squared times x, what is my coefficient? Negative 1. Good. Which is less than 0. So even degree means they both point in the same direction, right? Lead coefficient means they're both pointing down. So make sure your graph right now is in pencil if you're not drawing in pencil. This whole lead coefficient thing makes sense with what we learned about quadratic functions already. Ax squared plus bx plus c equals 0. If a is positive, it points up. If a is negative, it points down. 2, I'm going to find the x-intercepts. Okay, how do I do that? So it is all equal to 0. So here, in order to solve this, we factored it, right? And then we each term equal to 0. This one's already factored. It already saved us a ton of work. This one's already factored. So now we can just set each term equal to 0, right? Negative x squared equals 0, x plus 2 equals 0, and x minus 2 equals 0. So I solve that. I divide by negative, take the square root, I get x equals 0, x equals negative 2, x equals positive 2. So I'm going to put those on my little chart. Okay, 3, let's do y-intercept. What do you think the y-intercept is, just looking at this? 0, 0. I already found the y-intercept. I don't need to do that again. We know for a function it has to pass the vertical line test, so I'm only going to have one y-intercept. I'm only ever going to have one y-intercept. I already found it, so don't do it again. Right? Yes? Okay, 4. What do you think about symmetry? This one I can't really tell, right? Oh, I didn't talk about roots for this, or multiplicity. So what's the multiplicity of each root? This here is multiplicity 2, so it touches. These are multiplicity 1, so those cross. All right, so we can kind of get a picture, right? Multiplicity means connecting this with this dot is going to be like this. Connecting this with this dot is like this, right? I keep saying dot, but it's a point. So connecting the end behavior with this point, using multiplicity, it's going to cross. Connecting this one, this end behavior with this point, it's going to cross too, right? At x equals 0, it touches, so it's going to look something like this. So I pretty much have the outline of my function, right? I have the outline of my function. Right? So 4, is this looking even? Is this looking odd to you? Even is mirrored over the y-axis. Odd is mirrored over the origin, so it's over the x and over the y. Huh? It's looking even to me, right? So we can check to see if it's even. If we got something like this, having end behavior like this, the only thing we would check is if it's odd, right? But we saw we have the mixed, so that's okay to say it's neither. Here, I am thinking it's even, right? Because it looks mirrored. So let's check. So even is f of negative x equals f of x. So let's plug negative x in. This one's a little tricky. So negative x squared stays the same. What happens here? Can I factor a negative 1 out of this? Is that okay? Can I factor a negative 1 out of this one? Is that okay? So this is a little bit much, I think. Is this a lot? So then I would have this negative times this negative. I would factor this negative out. I would factor this negative out. A negative times negative is positive. So they are the same. Right? So I factored out the negative. So the thing is that it is even. It even looks like that, right? While I'm drawing. Okay, so now let's do 5, which is turning points. So it's a degree 4 polynomial, so I have a maximum of 3 turning points. So look at what we've drawn so far. I haven't connected the dots. I haven't connected my information. But if I connect it, do I have more than 3 turning points? Well, here I'm changing from increasing to decreasing. Here I'm changing from decreasing to increasing. Here I'm changing from increasing to decreasing. That's 1, 2, 3 turning points. So I'm doing well, right? So let's connect the dots. So I'm leaving this a little bit messy so that we can see the different parts that we did. All right. So then we'll start the next